Hello, everyone. Nice to meet you over this virtual conference. Metaflow is a human-centric machine learning platform at Netflix. We open sourced the Python package earlier this year and just released the R package a few weeks ago. Today, I'll talk about the Metaflow R package, which provides a human-centric data science experience for the R community. I'll first go through a case study to explain what are the problems we want to address with Metaflow R. And then I'll introduce what is Metaflow and the basic features and concepts of Metaflow. And I'll come back to our case study and show how Metaflow can help. Let's first go through a case study for developing data science projects in R. Here is our data scientist. Our first step is to define the problem. In our case, let's say, for example, we're working on prediction and causal analysis for user retention. The next step is to choose the data science ecosystem for our project. Here, our data scientist decides to use R. Let's see why we care about R. First of all, R has this tidyverse package system that's really good at data wrangling and visualization. There are tidyverse packages for data I/O, data cleaning, data transformation, data visualization, and dashboarding. All of them work very nicely with each other. There's also a data science-oriented IDE, RStudio. This gives you easy access to an editor, an interactive R console, variable explorer, visualization, help, docs, and file directory. All of them in the same place, very convenient. It's also easy to present results in R using the R Shiny app. This is an interactive dashboard that's very powerful when combined with visualization tools in R. Also, R has a rich set of libraries for statistical computing. For example, variable selection, statistical inference, causal inference, survival modeling, non-parametric regression, and other topics. Nowadays, I would say it's pretty common to release new algorithms in R for researchers in statistics community. Okay, so this is why we care about R, and our data scientist decides to use R. The next step is data preparation. We have an R script that pulls the CSV tables from two upstream data tables. We're running in a typical 8-core, 16 GB workstation. Luckily, the datasets are not so big. They are 2 GB each and they can fit perfectly in memory. The next step is feature engineering. Our data scientist has a lot of clever ideas on how to compute features from the raw data so they have high predictive power. Here is the feature engineering script in R, and this is the generated feature set. But unfortunately, the feature set has too many columns, and it doesn't fit in memory anymore. As a result, we're hitting out-of-memory errors. So our data scientist needs a bigger workstation. Requesting a new workstation takes time, but after some wait, we get a bigger machine. Now we need to set up the development environment in the new machine and copy all of our previous project data to the new machine. We also need to document exactly what computation resources are needed so that colleagues can easily reproduce this project down the road. This whole infrastructure migration process is pretty time-consuming. Now we're finally building models. The models.R script takes feature set and build models, which are saved locally. After we have the first model, we want to iterate on features and models to improve accuracy. This is quite common because features and models need to work together. For example, linear models don't handle features with heavy tail distributions very well. You can apply a log feature transformation to avoid the heavy tail feature distribution for linear models. Here we have two versions of compute features.R. One is in red, one is in blue. Each one produces a local feature set. The R script is version controlled in Git, but not the feature set because they're too big. We will try the first feature set, the red one, with a few versions of model. And then the blue one, the second feature set, with some other versions of the model. Now we have saved a few models locally. When we look at a single model file, how do we know which version of compute feature script and which version of model script actually produced this model file? So now we need some kind of spreadsheet to keep track of the experiments and manage the operations. This is very error-prone and time-consuming as well. What's more problematic is that we could unknowingly override a local feature set from a wrong script. So even the spreadsheet won't save us in this case. Let's say we're able to manage all this hustle. Now we need to scale out parameter search to tune learning rates and other parameters. One common way is to write a script to submit parallel jobs to a managed compute cluster. But first of all, we wonder how to move all the data needed for training to the remote cluster machines. If you're lucky, your cluster machines may be able to read data directly from your workstation, if you have something like network file system. We also need to ask where to write the training results. If we're writing to a central location, we need to manage the right path to avoid overwriting. We also need to keep the model script and the computation resource requirements in sync so that it's easily reproducible. And we need to deal with platform exceptions, such as timeout due to the occasional long wait time for the cluster. This is all about DevOps. Our data scientists would rather spend more time working on models and features. Okay, after all this trouble, we finally have a great model. You see, the training and testing loss goes down and accuracy goes up. But bringing good work to production is another game. Sharing results with colleagues so they can easily reproduce is not easy. We need to write instructions on how to run each script, in what order you should run them, and what arguments you should use to run each script. If my manager or colleague wants to inspect my feature set, I'm not sure how to share this large data set and how to keep them updated on the new results. It's also difficult to schedule a periodic model retraining in a production environment. Metaflow is designed to solve all these problems mentioned above. Now let's introduce the basic concepts and features of Metaflow. Data scientists usually care more about the upper stacks, for example, model development and feature engineering, and they care less and less about the lower stacks. Metaflow focuses on the lower infrastructure stacks, and we focus on the developer experience for the data scientist. Let's check this three-step Metaflow example. We first pull the data, and then run some analysis, and finally summarize the results. With Metaflow R, the code will look like this. You have 3 steps. Each step specifies the step name, the R function that needs to be executed, and the name of next step. And we chain them together using the pipe operator. In Metaflow, the computation is broken down into a DAG, and you can add branches in the DAG if you need to. Branches will translate into parallelization. These are the R functions for the steps needed in here, here, and here. Each step in Metaflow runs in an isolated environment. They can either be a local process or a remote execution task. Metaflow currently integrates with AWS batch compute environment, and users can choose any instance types according to their need. This is really powerful because I can simply do the development on my laptop and have almost infinite amount of compute power connected to my laptop. And the best thing is that I can choose to run my code on local or remote machines with zero change in R function implementations. And even if we run part of the computation on a remote machine, it just feels like running locally. In some sense, my laptop is converted into a supercomputer. We can specify computation resource requirements natively in R using the decorator here. This is how we make part of our flow run on AWS cloud instances. This batch decorator here says we want to run on the AWS batch remote compute environment. You can specify memory, CPU, and other resources here. Code and data created in each step are persisted together as immutable data objects. In some sense, code almost becomes a description of the data, and they are both contained in the Metaflow step. Because data objects are immutable, we don't need to worry about accidental data overwriting across runs. Variables without self $, are not persisted, and their lifetime ends when the step ends. All variables in self $sign are persisted as Metaflow artifacts, and they're accessible in downstream steps. Metaflow artifacts are automatically versioned for each run. They are stored on the global data lake in AWS S3. Here, our code and data are persisted together and also versioned together. By doing this, we have built-in data lineage within the flow, which tracks the data origin, what happens to it, and where it moves over time. You have read-only data access to previous steps artifact in the current run across local and remote steps. For example, self $sign data here is created in a local step, and it is used later on in the remote step. And the self $sign results is created in the remote step and used in the local step. Reading data from a previous step is straightforward. You don't need to worry about the path of the data files. Referring to self $sign variable names gives you the data generated in the previous step by the current run. You can also read artifacts from any step in the past run using Metaflow client, simply by referring to the step name and run name. Metaflow also tries to be friendly for debugging and quick iterations. If your computation fails in one step, or if you made a change to a step, Metaflow allows you to resume from this step using the data from previous steps without needing to recompute from start. This is pretty helpful for quick iterations because here you can think of each step as a managed checkpoint. If we do checkpoints manually, we have to worry about versioning and managing the file name and the path of intermediate data. Having steps as automatic checkpoints is pretty convenient. This is the idea of Metaflow. We take care of data warehouse, the compute resource orchestration, job scheduling, project architecture, versioning, and model operations. We hope our data scientist users can move very fast on the top two layers. With Metaflow, the data scientists at Netflix are able to quickly iterate and move data science projects from development to production in relatively short amount of time. Ideally, we want time to first production in days and not months. Let's come back to our previous case study and see how Metaflow can help. With Metaflow, our data scientists can just run the data pooling in parallel on local workstations, run feature computation on one big AWS instance, and parallelize parameter search over many AWS instances, all together in a single flow. In this way, we're able to focus on data science, not DevOps or infrastructure. Using Metaflow, there is no need for infrastructure migration in the beginning when the feature set grows too big. We can simply use the batch decorator to specify where to run the task. The dataset is also stored directly on AWS S3. Metaflow also takes care of compute orchestration and scheduling of the DAG. And very importantly, our code, feature sets, and model files are all version controlled and always in sync. So it's always clear which version of the features and model script actually produced a model file. Here's how simple branching works. At the start step, you would just need to specify the next two steps, and we will run the two steps in parallel. When they're both finished, we will run the join step, compute features. This is how we do parameter search very easily with Metaflow. We first define the parameters you want to search with. And in the step definition, you can use for each to specify the name of the for each variable. In the next step train model, there will be many parallel tasks, each task running the same code here. And you can use self $sign input to get the parameter assigned to each task. You can check our docs for other topics such as organizing projects, sharing results with safe reproducibility, and scheduling flows for production. Here's our doc page. We are open source on GitHub. Check out our doc and feel free to chat with the team in our Gitter channel. Thank you for watching, and please let us know if you have any feedbacks for Metaflow.